We are presently studying the chapter based on d block elements, and from the past few days we have been discussing the general trends in the properties of transition elements. We'll continue with this topic only, and today we'll be discussing a new property of transition elements. But before starting that, let us take a look at the periodic table one more time. रोज quick revision हो जाता है कि which part of the periodic table are we studying. There is no harm in that. From group 3 to group 12, this part of this modern periodic table is the D block. And I also want you to quickly revise inside your heads the difference between the D block elements and the transition elements. We did study about in this generalization that how every transition element is a D block, but every D block element is not a transition element. It is very important to remember that definition, and the reason also why all elements are not transition elements, because अब जो आप properties पढ़ रहे हो, these properties are shown only by transition elements. They cannot be shown by all D block elements. Cadmium, zinc and mercury do not show these properties because in their atomic and their most common oxidation states they have 3d10, 4d10, 5d10 configurations respectively, zinc, cadmium and mercury, right? So वो जो आपका पहले मैंने presentation में सारा introduction दिया, उस चीज़ को अच्छे से revise करना है, तभी जाके इन properties को आप समझोगे भी and you will retain them also in your memory. Now today's property, one of the most fascinating properties of transition elements is that they form colored compounds, right? They're ionic as well as they're covalent compounds. They are colored, and these compounds are colored both in solid state as well as in the aqueous solutions. Now I've taken this picture from internet and you can see that नाम लिखे हैं elements के and उनके क्या क्या colors हो सकते हैं, but what is important is that जो oxidation state in test tubes पे लिखी है, you will have to remember the oxidation state, because the color given in this picture for every transition metal ion is relative to that oxidation state only. Like copper, यहाँ पे जो ये shade of blue है, this shade of blue is only possible if copper is present in +2 oxidation state. It will not show this color in the +1 oxidation state. We'll understand the reason why they are capable of forming colored compounds, and I guess we'll come back to this picture. Now after this chapter we'll be doing a chapter based on coordination compounds, and उसमें हम एक theory पढ़ेंगे, crystal field theory. ये जो explanation है यहाँ पे कि why coordination compounds form colored compounds, it's basically based on that crystal field theory only. But right now we cannot study the theory in detail. I'll give you a quick introduction, and जितना हमें इस वक्त चाहिए होगी information about that theory, we'll talk about that much only. Consider this, forget about this right now, we'll read this out later. यहाँ जो भी मैंने description में लिखा हुआ है. Look at this diagram. Imagine these 5 d orbitals are the orbitals of an isolated atom. अभी bonding नहीं हुई है. The atom is isolated. As long as the atom is isolated, these 5 orbitals are degenerate. You know the meaning of the word degenerate. They are of equal energy. But when the anion approaches, यहाँ मैंने anion and ligand भी लिखा हुआ है. Ligand again is a term of coordination compounds, right? You're not aware of this terminology yet, so let's stick to the more general word anion. When an anion approaches, it can be an oxygen atom, it can be an atom of chlorine, it can be atoms of chlorine depending on the valency. When these anions approach, the first thing that happens is that these 5 d orbitals, they lose their degeneracy. They are no longer of the same energy, but they are split into 2 sets, a set of higher energy and a set of lower energy. Crystal field theory में इसको crystal field splitting कहते हैं. And as you can see, the energy difference between the 2 sets is delta E. It isn't much, बहुत ज़्यादा energy difference नहीं होता है. So electron can actually jump from the orbital of lower energy to the orbital of higher energy, and to do that energy तो required है. It is not much, but it is very small, but it does require that energy, and it can absorb, since it's a small amount of energy, it can absorb that energy, which will be a light of particular wavelength, and that falls in the visible region of the spectrum. Kam energy chahiye, as I said so many times, so that light is absorbed from the visible region of the spectrum, and the electron jumps from the orbital of lower energy to the orbital of higher energy. Now also from the classes of this last year, you know that excited state is short-lived. Very quickly ये electron वापस ground state में आएगा, and when it will come back, it will emit that extra energy जो इसके पास होगी. Rest of the energy will be emitted back by this electron, and that is the color of the substance. The light transmitted by this ion will become the color of the substance. It's very easy. Loses degeneracy, splits into two sets. Electron jumps from lower energy orbital to higher energy orbital, and when it comes back to its ground state, the light it emits, that transmitted light, becomes the color of the compound. Now this is possible only when there is an incomplete d subshell. Splitting होने के बाद भी अगर the configuration is d10, it is not possible. Electron cannot jump from one orbital to another. There has to be some vacant space for an orbital to jump from one place to another, and that is possible only when there are only 1 to 9 d electrons, not more than 9. That is why this property is specific to transition elements and not to all d block elements. Let's go back to this color part. So again, energy absorbed in visible region, that is why the transmitted light becomes the color of the compound. Now which color is this transmitted light? We have a color wheel. ये आपको पता होगा color wheel होता है. It's a wheel of complementary colors, and तीन primary colors है, blue, green and red इसमें है, and इन्हीं के जो बाकी complementary colors है उसी पे बना हुआ एक wheel which is called as the color wheel. For example, if a substance absorbs wavelength corresponding to red light, the transmitted light जो होगी वो fall करेगी opposite to red in this color wheel, and that's the shade between blue and green. This shade, the exact shade of copper salts when copper is in +2 oxidation state, right? And that transmitted light which falls in the greenish blue range, that becomes the color of the substance, right? This diagram is, again, I have taken this diagram also from internet, quite descriptive. You have degenerate 5d orbitals, then anions approach, there is a loss of degeneracy, then there is jumping. Jumping is possible only when there इन्होंने 9 दिखाए, maximum 9 ही हो सकते हैं, 9 या 9 से ज़्यादा 9 से कम electrons होने चाहिए, then only the jump is possible. And that is how the compound, the salt of the transition metal is colored, right? Now as I said right in the beginning, I'll get back to this picture. You know why they are colored. Now you know that. It is because of DD transition. Okay, one more important thing in this is that I have written most of the transition metal compounds are colored due to DD transition. This is DD transition, what we studied, jumping from one d orbital to another. But I have written most of them, not all of them. In our Zoom online classes, we have already studied about K2Cr2O7, potassium dichromate, and KMnO4. And there I told you that the orange color of K2Cr2O7 is not because of DD transition. Purple color of potassium permanganate is not because of DD transition. The reasons are different there. We have discussed it already there. Charge transfer क्या होता है, कैसे होता है. But that is why I have written most of them. Not all of them. There can be sometimes different reasons for the color of the compounds. However, we will continue with this generalization that mostly they are colored due to DD transition. Coming back to this, very important to remember. जैसे मैग्नीज आयन ही आप ले लो, +2 में pinkish है, light pinkish shade, and +7 में it's dark purple. It is the same element. These are the two oxidation states of the same element, but there's a color difference, right? यहाँ पे तो शेड का ही डिफरेंस है. यहाँ पे आप आ जाइए कॉपर पे, +2 ऑक्सीडेशन स्टेट में दिस इज द कलर, अ शेड बिटवीन ब्लू एंड ग्रीन. But if it is present in +1 oxidation state, there is no color, because in +1 oxidation state its configuration is 3d10. There is no possibility of an electron jumping from one orbital to another. There is no possibility of DD transition, thus there is no color. Titanium has this purplish blue, something between blue and purple color only when it is in +3 oxidation state. Its another oxidation state is +4, but in that +4 oxidation state it is colorless, because in +4 oxidation state its configuration is D0. Electron होना चाहिए, at least 1 तो होना ही चाहिए जो jump करेगा from one orbital to another, right? So electronic arrangement देखना पहले बहुत important है, oxidation state देखना important है, then only you can decide which color will be the color of the compound of that transition element. Like chromium के आप देखो तीन shades है, +2, +3, +6, right? I have added one more slide, I think. Yes, here it is. It is due to DD transition in most of them, and the color depends finally on the oxidation state. This diagram is kind of elaborate. You can see zinc plus 2 oxidation state, इसकी एक ही oxidation state है. Zinc atomic state में भी 3d10 है. इसकी जो most common oxidation state है plus 2, उसमें भी 3d10 है. Thus it is a D block element but not a transition element. That is why there is no possibility of DD transition. There is no color. Similarly, in other cases, you have cobalt in so many oxidation states, and you can see which color it shows in which oxidation state. We have iron, one of the very important elements. इसके जो compounds हैं, they can be greenish tinge उनका होगा. Then your iron is in +2 oxidation state. You're talking about the ferrous ion. But if it is a little rustish, rust का हल्का सा color होगा, it is the ferric ion. It is in +3 oxidation state, right?